Hello everyone, I hope you are all doing great. Good afternoon. Today inshallah I will continue our optimization journey that we started in the previous lecture. Today I will talk about the second type of optimization problems, which is constrained optimization. So in this lecture we are going to optimization with equality constraint. This is really a very important topic to be considered, and we will continue next week inshallah. I want you to know that the formulation of these problems will contain the function to be optimized, either maximizing or minimizing, and we did go through this in the previous lecture. So it is either maximizing your profit or revenue, or minimizing your costs or efforts or whatever. In this case, or today's case, it will be subject to certain constraint, certain equation to satisfy, or a couple of equations. Usually, the number of unknowns or decision variables should exceed the number of constraints at least by one, just to give more freedom in choosing the optimal solution. So we will deal with two maximization problems. The first of them is maximizing or minimizing, as I told you, optimization, a function f of x or y, which is a function in two variables, subject to a constraint of the type g over x or y equal to 0, or extending this problem to the three dimension. So I would have x, y, and z, which is a function in three variables, and also subject to the constraint of g of x, y, z equal to 0, as you can see. These are called constraint optimality, and the explanation is I want to optimize my function, okay, on a certain curve or on a given curve. This is why you can see, we see that f has at x naught, y naught, an absolute maximum or minimum point restricted to the curve in specific, which is the constraint that we are dealing with, as you can see. So it's a some segment of this curve just within the condition, and it extends to both sides, as you can see. What I want you to understand is that the optimization problem subject to equality constraint, it has a lot of application. The most well-known or famous problem, it is the consumer problem. That's a very important problem. You will feel it's actually you or her or whatever. So if I want to, the consumer problems comes to, I need the maximum use of my utility, but my utility under certain constraint. Maybe this constraint is a budget constraint. So once more, in economics, the consumer problem refers to how a rational consumer want to have the best of his journey, has the best computer that his hand can touch or can get, the dream car that he's dreaming about, it's the dream house or the engagement ring. So it is all what you want to have. Of course, you are maximizing your need. I need the best ring that I can reach. I need the maximum income that I can have, and so on. So in economics, the consumer problem refers to how a rational consumer chooses the best combination of goods or services to maximize his utility, his desire, his satisfaction. Okay, given their limited budget. Usually you will have a limited budget. I need a car and a house. I need the best car and the best combination of both of them, under the condition that my budget is limited to 1 mil, 2 mil, and so on. So this is, as I told you, maximizing your function subject to two variables or two decision variables or three decision variables, and subject to a certain constraint, as you can see. So I need the best solution to any of my needs, but under this constraint that I can't break or I can't violate, or my solutions are not going to be visible. There is a lot of methods to use this to reach a solution of such a problem. So this is mainly the objective function. As I told you, this is a constraint optimization of the equality type. I will have to satisfy my visible region by satisfying these conditions, and so the solution will be accessible. So we would like to find the best solution, as I told you, in the visible solution, satisfying the equality set of constraints. The number of decision variables must be greater than the number of equality constraints, as I told you, in order to have some freedom in the choices of the solutions. There are plenty of methods to use. We will consider three main methods. The first of them is the method of substitution. Some of these type of problems can be solved easily by converting them into unconstrained optimization, and that's the first method that we will use. We will use how to change the setup of your problem to be unconstrained if it is applied, or just to use a graphical solution, or to use the Lagrangian method. They are all close to each other, very close to each other. So let's try each one of them. I will go through the substitution method by considering this problem. I need to maximize f of xy, which is x times y, and it is subject to the constraint x plus y is equal to 6. In order to do this, all I have to do, the bottom idea, the bottom line, is try to make a substitution using the constraint and the substitute, or make it embedded in the objective function. So as you can see, in this case, we could incorporate the constraint, the objective function, and the transfer my optimization problem. Instead of dealing with a constraint optimization problem into unconstrained. So simply here from the given condition or constraint, I can get y is equal to 6 minus x, as you can see. Then I will take this substitution and substitute in the objective function. And in this manner, instead of having this is the maximum, or this is the function to be optimized, and that's the condition, both of them are all together in this unconstrained problem, 6 of x minus x squared. Once I have this function which is right to be optimized, it's going to be really very simple. All I have to do is to follow the main steps of functions in one variable, which means I will get the first derivative, but the first derivative equal to 0 in order to get critical points, then differentiating more to second derivative, substituting, blah blah blah, as you know. So the first step is to get the derivative of this function, which is going to be 6 minus 2 of x equal to 0, both the first derivative equal to 0 or the gradient vector equal to 0. From here, I will get that the critical point or the stationary point is at x equal to 3. Remaining to check, after getting the first derivative, which is 6 minus 2x, the second derivative, or I'm searching for the first non-null derivative, and according to that I will continue. So differentiating once more, you will get that f double dash is non-null, it's a negative. So at x equal to 3, we will have a maximization problem or a maximization. So if I need to know the value of the function when x is equal to 3, it's actually really very simple. All I have to do is to put x is equal to 3, so y is equal to 3. I have x and y, multiply them together, then your function maximum value is going to be 9. So in this problem, I've succeeded in changing the constrained optimality problem into unconstrained optimality problem, and solve it till the end of it, determining what's the critical point and what's the nature of this point. More examples on this. If, as I told you, if f of x, y given the g of x, I need these steps if I am formulating my problem. So the first is to reduce the constraint optimization problem involving two variables and one constraint. The second step is to start, as I told you, reduce both of them together in one problem. as the note is given to you. So if I look to this problem, I have x plus y, which is the function required to be obtained, but through or subject to 2x squared plus y squared equal to 4, which is an equation of a circle. So all I have to do now is to make the substitution. I can get the value of y as a function of x. So y squared is going to equal to 4 minus x squared under square root. Now I get the value of y, either positive or negative. So I will take this relation and substitute in my optimization function. So if y is greater than 0, I will take the upper wing, which is the root of 4 minus x squared, making a substitution. That's my objective function. It's an x plus the positive of this root. If y is less than 0, so I will do exactly the same, but I will take the lower wing of this function. So it's gonna be x minus the root of 4 minus x squared. Now I've changed my constrained optimality problem into unconstrained optimality problem. They will follow the same steps as the previous one. It's just two problems actually. We divided our one problem into two problems. Each one of them can be exactly solved according to our scheme. Get the first derivative, put the first derivative equal to 0, seek the first non-null derivative at the stationary point or the critical point, and according to it, you will have your classification. So if I started with the first function, x plus the root of 4 minus x squared, and start differentiating, this is gonna be 1. This is gonna be half 4 minus x squared to the power of negative half times negative 2x. That's the derivative of, or the first derivative. Of course, I will put it equal to 0. Once you put this equation into equal to 0, it is really very simple to find the solution, because simply it will be 1 is equal to 2 over x divided by 2 over 4 minus x squared. Just eliminate these two guys together, make a cross multiplication, so x is equal to the 4 of minus x squared. Square both sides, so it's going to be 2 over x squared equal to 4, which leads to x squared is equal to 2. That's x is positive or negative root 2, and those are the steps, as you can see, if I want to solve this problem, as you can see. Just give me just less than 1 second. I will try to get, yes, okay, very good. So as I told you, those are the main steps in front of you. Okay, so once more, I will try to analyze and getting the stationary point or points from this relation. In this case, I will have, as I told you, x is equal to positive or negative root 2, so I will have probable two values, the positive root of 2 and the negative root of 2. The second step is just preparing to substitution, but I will go to get the second derivative. Now I need the second derivative of this function, which is x over the root of 4 minus x squared, just squaring the denominator, getting the derivative of the numerator times the denominator minus vice versa, which is the division rule for the rational functions. Okay, this is my second derivative. I will substitute by root 2 and the negative root 2 in this relation. Once you try to substitute by root 2, the value is less than 0, which means at root 2 you will have a maximum point, as you can see. As x is equal to root 2, I will substitute in the main function, and so at this, it will be the value of the function, it will be the greatest one, it's going to be 2 root 2. Same procedure, same steps can be followed, but with the other branch, which is x minus the square root of 4 minus x squared. But it's exactly the same, just differentiating. The only difference is in the sign in front of the square root, as you can see. and then I will rearrange and get the value of x. Also, x squared is positive or negative root 2. I will take the first derivative and differentiate once more. This is going to be cancelled. And also, I will apply once more the division rule for the rational function. And that's going to be f double dash. Then I will substitute instead of x by positive or negative root 2. And the negative value is greater than 0, which means it's a minimum point. So using this problem, if you remark, I started with the optimization problem with an equality constraint. Then making the substitution to change it to be an optimization problem, but unconstrained with the steps of, with the use of calculus. As you can see, it's really very easy, it's not that tough. I believe I have another problem, this problem also, which is required to minimize x squared plus y squared subject to y plus x equal to 2. Similar debate. So the main idea, I will get y as a function in 2 minus x. Then I will make the substitution, and once more changing my problem, instead of being optimization with one constraint into unconstrained optimization, as you can see. Then I will start following the regime that we did. We will start getting the first derivative, put it equal to 0, critical points at x equal to 1. Get the next derivative, next non-null. It's going to be the even second derivative, which is greater than 0. And so it's a minimization point for this problem. As you can see, it's really very simple. If we back to the initial problem and make the substitution, we'll get the value of the function. I want you to know that, however, not all the equality constraints problems can be converted into unconcentrate ones. So we need approaches to solve this type of problems, because not all of them we can use this technique. This is why we will introduce the other two solution methods. The second solution method is the graphical representation. It's really a very successful method, and it depends on the following. Of course, it's successful once you have just a function in two variables and with one equation. It's going to be really very handy and very easy to do. So in case of optimization problem with two decision variables and one equality constraint, it is possible to use the steps. The steps are really very simple. All I have to do is to try to get the level curve of your function and equate it by the gradient of both of them, the function and the condition. At the optimality point, they are equal to each other, and that's the calculus key that I will depend on. The graphical key is just trying to draw the main condition and draw the given function and try to move it upward or downward till you reach the maximality point. I believe if we did go through the steps of a problem, or to see it on a problem, is going to be really very nice. So the first step, let's present the set of all solutions that will satisfy the constraints. Then the general expression of the level function. Number 3, with the help of the level curve and the visible area of solution, we can find the solution of this problem. So this slide actually summarizes the steps. Okay, let's see this problem. I need to optimize x plus y, which is subject to x squared plus y squared equal to 4. It is, I've tried to take the same problem that we already had in the substitution and see how to deal with it with the graphical solution. So simply all I will do is try to find the region. The region or the curve that I need to satisfy is x squared plus y squared equal to 4, which is actually very simple. It's an equation of a circle. It is an equation of a circle, as you can see. So x squared plus y squared equal to 4. It is the equation of a circle with radius 2, as you can see. Now I will get the level curve equation of my optimality, which is x plus y equal to k. That's the level curves, set of level curves that I will deal with. Okay, so y is gonna equal to k minus x. So the start, if k is equal to 0, it's gonna be y equal to negative x, which is just simply this line at k equal to 0. If k is equal to 1, the line will be upper or to the right side of your line. So I will try to move till the last line that will touch my circle and from the other direction. Of course, this is the direction of optimality. If I'm moving in this direction, which is perpendicular on y equal to negative x, if I'm moving up, I will be maximizing. Moving down, I will be minimizing. That's the direction. So it's really, in order to do the calculus of this issue, it's really very simple. All I have to do, as I told you, this is my function, x squared plus y squared equal to 4. I will start with the level curve 0, which is y equal to x, or using this relation, when x is equal to y, I will make the substitution. Of course, I'm using y is equal to x because this is y equal to negative x, my level curve, and y is equal to x, the perpendicular direction, which is the direction of the increase. That's the equation that I will depend on. So replacing y by x, I will have 2x squared equal to 4, and from then x is positive or negative root 2, and this is why this is y is equal to x. Just a second. This is y equal to negative of x, and I will move it till the end, which is gonna be at this point at x is equal to root over 2, and that's the minimum at negative root 2, which are the same solutions that we already have in the analytic solution. As you can see, the graphical solution, it's very nice. It's well applied here in this problem, but it's not gonna be the case in other problems. In usually the calculus solution, it's more practical and it's more accurate to have. I believe I have more than one problem. So if I look also to this problem, the problem that we solved earlier, which is for x times y and subject to x plus y is equal to 6. So this is my condition or my constraint, which once more, this is the constraint, as I told you. This is the level function, which is x, y equal to k. So y is equal to k over x. It's gonna be a rational function, but according to the value of k, I will have a family of them. So maximize it at the tangent point between the level curve and the constraint. How to compute this analytically? We know at the tangency point between the constraint and the level curve, this is the point of optimality. In order to do this, in order to get the slope of the tangent, all I have to do is to get the gradient vector of the main function equal to some lambda in the gradient vector of my condition. And this is actually really very close to the third method that we will use just in a few slides. So once more, those are the family of curves of the rational function. Y is equal to k over x. According to the value of a, I will have these rationals in the representation of the rational function in the first and third. And this is the gradient vector of the constraint at the same point. They will be parallel to each other, so they will equal to each other. And that's the analytic key that I will depend on. So if we try to apply this on our problem we have f, which is xy, and the g, which is x plus y is equal to c. If I get the gradient vector for x times y, I want you to remark, this is the function f required to be optimized, which is xy, and that's g, which is x plus y equal to 6. So if I need to get the gradient vector of f, it's gonna be simply partial f, partial x, partial f, partial y, which is simply gonna be differentiating with respect to x is gonna give you y, differentiating with respect to y is gonna give you x, and that's the gradient vector of f. Here we go, y is equal to x. And if we get the gradient vector of g, which is differentiating with respect to x is gonna be 1, with respect to y is gonna be 1 times lambda. So from here, from this condition plus the constraint, I can solve them together and get the values of x, y, and lambda. So this means y is equal to lambda and the x is equal to lambda. These are two values. If you took these two values and substitute in the second equation, it's going to equal to 2 lambda equal to 6, which means lambda is equal to 3. Once lambda is equal to 3, I will substitute back. This is going to be 3 and that's going to be 3. So now I have the optimality point. It will happen at x and y equal to 3. And so now I know if I use these two values, multiplying them together, it will be 9 exactly as the substitution method did when we solved this problem earlier in the previous slide. This is really one of the simplest techniques that we can use. Also, we can generalize it. Also, that's another problem, which is I need to minimize x squared y squared subject to y plus x equal to 2. So same steps will be followed. I will try to get my gradient vector, which is gonna be 2 over y, 2 over x. This is the gradient vector of f, which is gonna be 2 over x, 2 over y. Okay, the gradient vector of the condition, which differentiating with respect to x is gonna be 1. Differentiating with respect to y is gonna be 1. So 1 times lambda, I will equate them, which means that x is equal to lambda over 2. Y is equal to lambda over 2. If you make the substitution here, you will get the value of lambda, which is 2. Substitute back in x and y, both of them are equal to 1. So the optimality will happen when x is equal to 1, y is equal to 1. If you substitute, you will get the value of your function, which is gonna be 2, as you can see. This is the second method. So now we have two methods, the substitution method and the graphical method. And you can see they are very, very close to each other. From this point in the graphical solution and the gradient vectors is equal to each other, we will use it to come to the Lagrange multiplier method, which is a generalization for the graphical method or the calculus that's used in the graphical method. It's really very simple. It depends on if this is your function to be maximized, and that's the object, that's the constraint to be satisfied. All I have to do now is to form this Lagrangian function. And the Lagrangian function is simply lambda of xy equal to the function required to be optimized plus both the condition as an equation is equal to 0. So it's going to be b minus g of xy times lambda. And then let's get the gradient vector, or let's optimize the Lagrangian function satisfying all of this. So all I have to do now is to differentiate L with respect to lambda, differentiate once more with respect to x, differentiate once more with respect to y. These are the partial derivatives, as you can see, for the Lagrangian with respect to lambda, to x, to y. Both them equal to 0, getting the gradient vector and both equal to 0, you will get the critical or stationary point. But here I will use the Hessian matrix of the Lagrangian function, which is given by partial 2L partial lambda square, partial 2L partial lambda partial x, and so on. Then according to the principal minor of this Hessian matrix, I will be able to classify the case of my problem if it is maximization or minimization according, as I told you, to the principal minor, which is of the last one with n minus b, where n, as you can see, it's really very simple, where n is the number of variables and b the number of constraints. Usually, if I'm dealing with 2 by 2, it is the 3 by 3 determinant. If the 3 by 3 determinant is greater than 0, then it's a local maximum. Less than 0, then it is a local minimum, as you can see. If we want to apply it, it's really very direct. This is the function, and then it's going to be lambda times 2 minus y plus x, as you can see. That's the Lagrangian. So once more, the Lagrangian is taking the objective function first, plus lambda, move those to the right, so it's going to be 2 minus y minus x. Then for this function, start differentiating with respect, get the gradient vector, which means I will differentiate with respect to lambda, with respect to x, with respect to y, and remark the order of derivative. That's exactly what we are going to do in order to get the gradient vector. With respect to lambda, with respect to x, with respect to y. So if I differentiate with respect to lambda, I will have 2 minus y minus x. If I differentiate with respect to x, it's going to be 2x minus lambda. If I differentiate with respect to y, it's going to be 2y minus lambda. Put them all equal to 0, as you can see. Now I have x is equal to lambda over 2, y is equal to lambda over 2. Use them and substitute in the condition, and then you will be able to get the value of lambda. Substitute back, you will get your results. So the solution, or the critical stationary point, it will happen at lambda equal to 2, and the both of x and y are equal to 1. And that's the third method that we used on the same problem. The substitution did well, the graphical did well, and also now for the Lagrangian. After getting the first derivatives, I will differentiate more in order to get my Hessian matrix. So it's a partial 2L with respect to lambda square, partial 2L with respect to lambda and with respect to x, partial 2L in partial lambda, partial y, and so on. This is the Hessian matrix. Of course, we have the number of decision variables are 2, the number of constraints is 1, so I will take the last principal minor, which is, as you can see here, doesn't depend on the value of the points, so it will be the same. Then I will evaluate the determinant of this function. If it is greater than 0, maximization, take care it is, if it's greater than 0, it is maximization. If it is less than 0, it's minimization. So try to get the determinant, which is going to be 0 times 2 times 2 is going to be 0. I'm using solace. Negative 1 times 0 times negative 1 is going to also be 0. 0 times negative 1 times negative 1 is also 0. Then minus. All of those times each other will give negative 2. Then those are zeros plus 2, but the general sign is negative, so it's going to come up to negative 4, as you can see. That's the value of the determinant. Since it is less than 0, then at the point x is equal to 1 and y is equal to 1, we will have a minimization point, as you can see. So the function is going to be minimum, and that's the value of the function. Steps are really very simple. Okay, once more, if I want to solve this problem. In this problem, you will need to read it and formulate your problem. That's an example of how it goes if I'm trying to explain my problem to someone and try to come to the suitable mathematical formulation. So here, it's telling you, suppose that we want to maximize the utility function u of xy, which is xy, where x and y are quantities consumed by two goods. The price of each unit of goods x and y is 2 and 1 monetary units respectively, and the available budget is 100, which means I need to find the optimal solution of x times y under the constraint 2 of an x plus 1y is equal to 100. So that's the formulation of my problem, replacing the mass word problem into an objective function and a constraint, equality constraint, as you can see. Now I am free to use any of the previous methods. I will use the Lagrangian method. Once more, it's really very simple. Try the Lagrangian. I will put the function, which is xy plus lambda, open your bracket, 100 minus 2x plus 1. This is actually what we did directly in the Lagrangian. Then I will get the gradient vector, which means I will differentiate with respect to L, with respect to x, with respect to y, putting the derivatives into zeros, as you can see. Now, if I differentiate it with respect to lambda, I will have my constraint, which is 100 minus 2x minus y equal to 0. That's the first. Differentiate with respect to x, so it's going to be y equal negative 2 lambda. Replace with respect to y, it's going to be x, that as you can see, x minus y. So it's going to equal to x is equal to lambda, y is equal to 2 lambda. I will use them and substitute in the constraint equation, from which I will get the value of lambda, which is going to be 25. I will resubstitute in the other two equations by lambda equal to 5, it will give you 50. 25, it will be 25. Now I have the solution. I will start to get the second derivative from the Hessian matrix by differentiating another time and differentiating each one of them in order to formulate my Hessian determinant. This is the second derivative of L with respect to lambda, the second derivative of L with respect to lambda, then with respect to x, the second derivative of L with respect to lambda first, then with respect to y, and so on. Then, as you can see, they are all numbers. So I will evaluate the value, and it's going to be the third one. Also, because we have two decision variables and just only one constraint. So it's the last principle that I will evaluate. Multiplying those guys is equal to 0. This is going to be a positive 2, and that's going to be a positive of a 2, which is 4. This is direction is 0, 1 times 1, 0, and negative 2 times negative 2 times 0. It's 4, exactly like we did in linear algebra in the first semester. Now I have the determinant, it's greater than 0, then I will have a maximum utility or maximum value of my function. I've added a couple of problems